Okay, so as I was saying before, C++11, the support for random number generation in C++, unless you were doing it using some external library, was based on the C standard library. So I think that more or less every one of you have seen something like this. You needed to include the C++ version of the C standard lib. Then you needed to initialize this random number generator with providing a seed. This is just a random seed. Then you can get a random number making a call to the rand function. And then you needed to use this macro, rand_max, that is a macro expanding to the maximum integer constant that was provided to you by this rand function. So in this case, you have basically a normalization of the random number generated, and you have a uniform distribution between 0 and 1. The problem with this way of generating random numbers was that the underlying generator of random sequences, of pseudo-random sequences, was unspecified, so you don't know basically which algorithm was used. And the second one is that in general it was a low-quality random number, which means that if you made some statistical analysis on the pseudo-random number sequence, you can see that it was not really random. There was some regularity, let's say. So if you're making some calculation like integral Monte Carlo calculation or something like that, it was not really a good choice. Starting from C++11, you have a better support, better native support for random number generation, and that is based on two elements. One engine that is a generator of pseudo-random bits, sequences, and another element that is a distribution, which is something that takes in input this random sequence of bits and gives you back a number that is distributed according to a given mathematical distribution, a Gaussian, binomial, Poissonian distribution, whatever. So random number generation in modern C++ is done exactly in this way, based on that two elements. And this is exactly this is a translation of the previous example that was done, let's say, using C support. And this is done instead using C++11. So you have to include the random header. You have to define a random number engine. In this case, we are using this default random engine. And again, I'm calling the constructor of that object providing a seed, which is the same number that I was using before. And then you have to define a mathematical distribution that is the one that will be used for the generation of real number, let's say. And in this case, is the uniform real distribution with double template parameter, which means that you will get double numbers as output from this random number generation. And these two parameters are, in this case, the minimum and the maximum value of the uniform distribution. These two parameters that you have to provide to the constructor of the mathematical distribution, of course, depends on the distribution itself. In this case, it's a uniform distribution, so you just have the minimum and maximum value. If you will generate a random number with a Gaussian, with a normal distribution, you will have to provide the average and the standard deviation, of course. It depends on the mathematical definition of the distribution. And finally, you can get the random number that you need for your calculation, just making a call to the operator with the round parentheses of the distribution object itself, providing the random number generator here. So you have a basic interface for this pseudo-random number, let's say pseudo-random bit generator that is a constructor. This is the one that I have already used in my example. This is a constructor that takes in input the seed for the generation algorithm. This is instead the default constructor. And then you can also define the seed during your calculation, during your simulation, if for any reason you need to change it by making a call to the seed method. And with the empty parameter list, you will just set the default seed number. Okay, this is something that maybe can be useful. Let's say that you need to generate different random sequences for the same code in different jobs. This is something common that if you need to run a series of different jobs to make the same calculation and maybe at some point to merge these results. Of course, you can, if you need to do something like that, like to split the calculation of an integral on multiple jobs, you cannot just replicate the same jobs for n times, because you will get the same random sequence, and then the results, of course, will not be statistically meaningful. You need to generate random numbers starting with, let's say, different series of random numbers, and for this reason, you need different seeds. This is something that sometimes it was done with C code, let's say, doing something like this. You can just initialize the random generator using some source of causality like this time function. The problem with something like this is that if you're submitting your jobs on a system like, let's say, on a cluster of PITSDINT or any other parallel system, let's say, you can get the same seed for different jobs, and of course this is not a good situation if you then need to merge these results to get the final number. With C++, you have with modern C++, you have this random device that is linked to a random device of the system, and it will give you a real source of causality that you can use to initialize the random engine. The thing is that there is no guarantee of which device you are using to get this seed. It depends on the implementation, and in some cases there is a string argument that you can use to define what is this source of randomness, let's say, that you can use for the initialization of your random engine. There is a list of available engines. In my previous example, I was using this default engine that is, let's say, a low-quality engine that gives you a fast generation of number, but you can get a better results from a statistical point of view, taking something more refined, like one of the generator of this list. The only thing is that you get, let's say, a better quality of random sequences. The problem is that it will be more expensive from a computational point of view, because the implemented algorithm for the random generation in this generator is, of course, a bit more complex. I don't know if you have some experience with the Monte Carlo calculation, maybe in Fortran or whatever. I guess that you have already seen RunLooks, because it was almost everywhere at some point in the past, at least in particle physics. I don't know what is your field, but it was everywhere. There are also some, let's say, advanced engines with more complex interfaces, where you can also define if you want to skip some blocks of random number generation, you want just to avoid some repetitions, and where there is something even more complex than just these default generators. And the default the generator of this list are special cases of these templated generators for particular parameter set. So if you really are into this kind of mathematical topics, you can have a look and get some more information. The engine have some additional properties that I think that can be important. Particularly the first one, you have the possibility to save and restore the status of the generator. This is interesting if you are doing, let's say, long calculation, and you need to print a checkpoint file. That is something that is needed. In this case, you can then print this checkpoint file that contains the status of the generator that can be restored in case something goes wrong with your simulation. You don't have to start from the very beginning. You can start from let's say from the last checkpoint of your simulation, just resetting the generator to the last printed status. So I think that this is important. And let's move to the distribution. There is a long list of available distributions that can be used with this generator, so you can get all this possible generation. You have a uniform distribution with the integer or real number. You have the Bernoulli distribution, Poisson, normal distribution, or sampling distribution. So it's a quite long list, so I guess that you can find what you need in this. list. The interface of these objects of the distribution is common for all these cases. Basically, they are templated in most cases on the type that will be returned when you do the real generation. So for the Poisson distribution, the default case for the template parameter is an integer. And for the normal distribution, the default case, if you don't specify that you want something else, is a double number. All these objects, all these distributions have the same interface concerning the generation of the real of the random number sequence. All implements this operator parenthesis method that takes in input the generator and gives you back the random number generated for that particular step. There is also another version that takes in input also the parameter set that characterize that particular distribution, which means that you can define you can define, for example, a normal distribution with these two input parameters. You want a normal distribution that is centered on 0 with the standard deviation that is 1, and then during the simulation, during your calculation, you can change the value of the mean and of the standard deviation just calling the second method, providing the new set of mathematical parameters for the definition of the distribution itself. So you can do something like this. You can have this this uniform distribution that has as a defining parameter the minimum to 1 and the maximum set to 6. Then you have to define a random engine. I'm using in this example the default random engine, and then you can generate your number just making a call to this method, providing only the first parameter, which is the engine. In case you want to change during the simulation the set of parameter characterizing the distribution, you can provide a new set of parameter, like the same thing that I'm doing these two lines. In that case, you are just changing for that particular number the definition of the distribution. So when you generate a new number without the parameter set, you will go back to the initial definition for the minimum and maximum value. And you can also change in a permanent way the parameter set using the param method and providing in input the parameter set for the distribution. This is the same interface, and this interface is common to all the distributions. Of course, we have also the getters method to access the parameter set of the particular instance of a distribution that you are using, which means that, let's say that you have a distribution, is again, in this case, a normal distribution with the average 0 and the standard deviation 1. You can get the parameters, the set of two parameters, making a call to this param method. And of course, the result will be stored in this P object. And this is a common interface to all the distribution. They all have the param method, but you can also have the access to the specific parameter with the specific name that depends on the distribution that you are considering. So in this case, since it is a normal distribution, we have the mean and standard deviation method that will, of course, will give you back the value of the mean value of the distribution and this standard deviation. Also, for the distribution, we have some additional features, like you can print. The most important one is, of course, in this case, also the possibility to print the status of the distribution for your checkpointing file, so that you can go back to the last result and continue with the simulation. And I think that, yeah, that was the last one. It was a very quick presentation with only the basic features. So I guess that if you're already using this object, you already know these contents. So is there any question? Yeah.
This is a question really to anyone who might know. In many HPC applications, people are using so-called hashing or cryptographic random number generators, like random 1, 2, 3. And there's been some talk in the past about how these may be incorporated into the C++ standard library. I've not heard any news. Does anyone know if this is still something that may happen?
Not that I know of. The only thing I'm being aware is basically reducing the complexity of this for common cases and go back to an interface similar to RAND, which I think happened in C++ 17. And but yeah, I haven't heard anything about adding new algorithms or new features. I think in all these cases, with random or with mathematical functions, the C++ 17 has this all these math functions. The question is usually from the vendors of compilers and libraries. They say, well, this is a lot of work for us. Are we sure that this is going to be useful? Why cannot just people download the library that they need and then just use them, right? Which is kind of reasonable. But and so yeah, so for the mathematical functions, it's been really hard to get the standard library developers to actually do that work. And
given that these have been available for C for quite some time, why were vendors so reluctant to provide them for C++?
Mostly because the developer of a standard library has always been a computer scientist, very smart and bright computer scientists, but they felt, especially for the math functions and also for some of these distribution, is that if someone finds a bug and say bit 17 of this Bessel function is wrong, then they will say, now what? Right? I don't have a PhD in numerical analysis. I don't know how to debug this thing. And so they felt it's too hard. And they finally agreed on doing it. I was actually quite skeptical that they would have done that at all, but they agreed to do it. So I guess they found some kind of some baseline implementation from C or something like this. But all right, no more questions? So what we were thinking of doing is to let you guys playing with the examples and in the repository, and then ask free questions, and basically end the course here. I think it's been pretty intense days, so I think it would be a good idea if you want to play with those examples. If you don't have the URL, I probably have it somewhere. That's interesting. So let me find it for you. So there is a folder in the, so you can play with the examples in code, but there's also a folder named exercises where you can find template exercise, share pointers, and threads. You can find the code that we have been showing during the presentations here. I think Anton code is not there yet, but I tried to get the code, and then yeah, I think this is the best use of the time for now. I don't want to overload you with more information that would be not very useful. Yeah, so I will be here, Christopher, Sam, and the other instructor, Anton too. yeah, we will be here. I don't know if Nora is going to leave or not, or you're going to stay here for a while. But yeah. So feel free to ask us any questions.